It is given the next information. This question asks you to explore the behavior and key features of cubic polynomials of the form x cubed minus 3cx plus d. Consider the function f of x is x cubed minus 3cx plus 2 for x is real and where c is a parameter, c is real. The graphs of y is f of x for c is -1 and c is 0 are shown in the following diagrams. A. On separate axes, sketch the graph of y is f of x showing the value of the y-intercept and the coordinates of any point with 0 gradient for I c is 1, 3 marks, I c is 2, 3 marks. So we need to consider c is 1 and c is 2 and plot two graphs of this function. Just using a calculator. And we also need to show clearly any points with 0 gradient. It means any points of maximum or minimum, and also y-intercept. And the required graphs look like this. The next, write down an expression for the derivative of f. So derivative becomes 3x squared minus 3c. 1 mark. C. Hence or otherwise, find the set of values of C such that the graph of y is f of x has I, a point of inflection with 0 gradient, 1 mark. To have a point of inflection, second derivative should be 0. Second derivative is 6x, and when it is equal to 0, x is 0. So at x is 0 is a point, there is a point of inflection, but we need there must be 0 gradient, so the first derivative is 0, which is 3 times 0 minus 3c should be 0, hence c is 0. So again, the point of inflection with 0 gradient, c is 0. Next, one local maximum point and one local minimum point, 2 marks. So there must be two turning points, and the necessary condition is that the first derivative should be 0, and to have two turning points there must be solutions, and there must be two solutions, and we can see that when c is negative, x squared is equal to the negative number, hence there are no solutions. But when c is positive, x squared is c and x is plus minus root c, it gives us two turning points, or actually it's just stationary points. But to have two stationary points, c must be 0. And the next, no points where the gradient is equal to 0, and hence when c is less than 0, derivative to be equal to 0 has no solution, so no stationary points, and hence no points with 0 gradient, 1 mark. Next, D. Given that the graph of y is f of x has one local maximum point and one local minimum point, shows that I, the y coordinate of the local maximum point, is 2 multiplied by c to the power 3 over 2 plus 2, 3 marks, and II, the y coordinate of the local minimum point, is negative 2 multiplied by c to the power 3 over 2 plus 2, 1 mark. So actually we need maximum and minimum points, and from this we can see that when c is greater than 0, x is plus minus root c, these are stationary points, and hence these are maximum and minimum, and how to find out which point is maximum and which is minimum. we can find the second derivative, which is 6x, and we know that the second derivative at the point is negative, hence it's maximum, and if the second derivative is at the point is greater than 0, it's minimum, or actually general form of the curve. We can see that maximum is to the left. So maximum x coordinate is negative root c, minimum x coordinate is root c, and then just substituting x value into expression for the function, we need just calculate that y max is negative c to the power of a half and cubed, so it's negative c to the power 3/2, and negative 3cx, so it becomes minus plus 3 c, and c to the power of a half, it's c to the power 3/2 and plus 2, and hence it becomes 2 multiplied by c to the power 3/2 plus 2 as required, and minimum is at it's c to the power 3/2 minus 3cx, so c to the power 3/2 plus 2, which is negative 2 multiplied by c to the power 3/2 plus 2. And actually our graph it's not required, but our graph looks like this. Maximum is at y coordinate is 2c to the power 3/2 plus 2. Minimum is at negative 2, y coordinate c to the power 3/2 plus 2. When c is greater than 0. Hence, for c is greater than 0, find the set of values of c such that the graph of y is f of x. It's actually this graph should be considered. And situation when c is greater than 0. Exactly one x-axis intercept, 2 marks. To have one point, one x-intercept, it may be that maximum is below x-axis and minimum is also below x-axis, so it may look like this: maximum and minimum. So we have only one x-intercept. But if we consider this expression, we can see that when x is greater than 0, this value is 2 or more. It means greater or equal than 2. It's always increasing value. So it cannot be negative, so this point cannot be below x-axis. And another situation is when minimum is above x-axis and maximum is also above x-axis, but this point is also always positive, so it's always above x-axis. So we need to consider that y coordinate of the minimum, which is negative 2c to the power 3/2 plus 2, should be greater than 0. And we can see that c to the power 3/2 is less than 1, hence c is less than 1. Just raise both sides to the power of 2/3. And the next, exactly 2 x-axis intercepts, 2 marks. Exactly 2, again, it may, in general, it may be like this, or like this, but since this value is always greater than 0, it's impossible. So the only possible situation is when minimum is equal to y value of the minimum is equal to 0. So it's negative 2 times c to the power 3 over 2 plus 2 is 0, and we can see that c is 1. The next, exactly 3 x-axis intercepts 2 marks, and exactly 3 it should look like this. This is always greater than 0, so minimum should be below x-axis, so negative 2c 3 over 2 to the power 3 over 2 plus 2 should be less than 1, and hence c should be greater than 1. Oh, 0, 0, 0 here. The next, consider the function g of x is x cubed minus 3cx plus d for x is real, where c, d are real. F, find all conditions on c and d such that the graph of y is g of x has exactly one x-axis intercept. Explaining your reasoning, so we need one x intercept, 6 marks. So this function, it's actually the same, but d instead of 2, so it just y-intercept actually changes. It becomes d instead of 2. But if we consider maximum or minimum, we can see that this value 2 or d in general disappears, and x coordinates of maximum or minimum are independent of d, and hence x maximum or minimum remain at the same x coordinates. But if we calculate y coordinates, we again substitute x into expression for g, and you can guess, or actually you can check or calculate again, but we will get absolutely the same, but d instead of 2. So it will be absolutely the same, but this point becomes 2c to the power 3 over 2 plus d, y-intercept is d, and minimum is negative 2c to the power 3 over 2 plus d. And we need again one x-intercept. So to get one x-intercept, let's consider this situation, that maximum, which is 2c to the power 3 over 2 plus d, is less than 0, so it's below x-axis, and or it must be at the same time minimum, which is negative 2c to the power 3 over 2 plus d, also must be less than 0. Hence d is less than negative 2c to the power 3 over 2, and at the same time d is less than 2c to the power 3 over 2. And this solution, these two regions intersect when d is less than negative 2 multiplied by c to the power 3 over 2. And actually c must be greater than what to have, to have maximum and minimum, and it must be greater than 0, because it's absolutely the same situation, and when c is less than 0, there are no maximum or minimum. and it may be that maximum is above x-axis and minimum is also above x-axis, and provided that maximum and minimum exist, so it's c is greater than 0. So it should be 2 multiplied by c to the power of 3 over 2 plus d should be greater than 0, and negative 2 times c to the power of 3 over 2 plus d also must be greater than 0. So d is greater than negative 2 times c to the power of 3 over 2, and d is greater than 2 multiplied by c to the power of 3 over 2. And we can see that the solution is d is greater than 2 to the power of 3 over 2, and c is greater than 0. And let's consider when c is 0. When c is 0, our function becomes just x cubed plus d. And what is x cubed plus d? It's just x cubed, which looks like this. It's x cubed, but x cubed plus d is just shifted d units up or downwards. It doesn't matter. So anyway, it has only one x-intercept as required, and it's independent of d. So when c is 1, it's independent of d. It has one x-intercept as required, so it's also solution, the required condition. And let's consider when c is less than 0. When c is less than 0, hence the derivative to be equal to 0, there are no solutions, so there are no maximum and minimum points, and actually our function becomes x cubed plus the absolute value of cx plus d. So it's actually the greatest term is x cubed, so it will be also similar to x cubed. And if we consider derivative of g, it becomes 3x squared minus 3c, and when c is negative, it's positive, and it implies that function g of x is always increasing, and hence it looks similar to x cubed, and there will be only one x-intercept. And we can see that it's also independent of d. And we can combine these two situations. So when c is less or equal than 0 and independent of d, there will be only one x-intercept as required. And also these two situations when c is greater than 0, d is less than this value, or when c is greater than 0, d is greater than this value. So the answer is this, and this. And that's all for this question.